Integration by parts is usually applied in fairly straightforward ways, like we've seen in earlier examples. There's some particular combinations of functions, though, that also arise frequently in physics and chemistry in particular, and evaluating their integrals by parts requires just a little tweak or a little trick that might not be obvious in the first go-round, so we'll demonstrate it here. In this function, we're integrating cos of x e to the x. And unlike the earlier examples, you'll notice that if we differentiate cos, we'll get sine. That doesn't make it simpler. If we pick e to the x to be our u, we differentiate e to the x, we get e to the x again. That's not simpler. So how will integration by parts help us? We'll demonstrate this by walking through this example. For the sake of argument, let's just let u equal the cos part. So the dv part will be e to the x dx. So we'll just plunge on ahead, integrate the dv part, differentiate the u part, and see what happens. We differentiate cos, we get negative sine. Dx, we'd have a dx, we bring it up. On the integral side, we get v is the antiderivative of e to the x, well that's just e to the x. Add our arrows, and our integral in is going to equal cos of x e to the x minus the integral of e to the x times minus sine x dx, and that equals cos of x e to the x plus e to the x sine x. Double negative out front. Okay, well, have we made things simpler? Here, I think we have to say not yet. I was about to say no, but not yet for now. Let's do one more step, and again, thinking of strategies, if we pick u to be e to the x, we're going to integrate sine. Well, that's going backwards the way we did it. What happens if we do it again, but we apply the same choice? We let u again equal the trig function, so this time the sine function, and we keep the dv as e to the x dx. If we do that and do our same analysis, take the derivative, take the integral, we're going to get du on this side is going to be cos of x dx, and on this side we're going to have v equals, again, e to the x. Okay, so our original integral is equal to e to the x cos x plus all of this stuff here, e to the x cos x plus this. Let's write that on the next page. So our integral of cos x e to the x dx can be rewritten as this cos plus a new integral. And this part here we just expanded, so we'll say cos of x e to the x again, plus this integral, and if we look at the parts on the last page, it's sine x e to the x, so plus sine x e to the x, minus the integral of e to the x cos x dx, e to the x cos of x dx. Now that doesn't seem particularly helpful at first glance because we just came full circle. Here's where we started, we got to here, and now we've got this integral. But if we're careful, we actually notice that this is our original, e to the x cos x, or cos x e to the x. This is also our original, and they're on opposite sides of the equal sign, with this one being negative, which means when we bring it over to the other side, we can actually say there's two of those. Two integrals of cos x e to the x will equal cos of x e to the x plus sine of x e to the x. And this is one of those counterintuitive things. We never actually finish doing our integration. We just say this is what we want. It's in an equation with other things, so we solve for it. The integral of cos x e to the x is going to be cos e to the x plus sine x e to the x all over 2. So it's a bit of a different way to look at integration, where we use a circular approach. In other words, we keep doing the same thing over and over until we get back to where we started. But with the way integration by parts works, if we keep the same choice of u and v as we go through this, we're going to get an opposite sign, which means that we can move things around, things won't cancel, and we'll have our integral equals some new formula. And that's, in fact, if we differentiate this, we would get cos of x e to the x.